In this final section of chapter 9, we first want to find a way of how to find the eigenvalues of an endomorphisms. We have seen a lot of about eigenvalues, about diagonalizability, but we always assumed that we kind of knew the eigenvalues. So we need to find a way of how to compute the eigenvalues of some given endomorphism. We will do so, and then we will also study how to kind of find out if a map is diagonalizable, and if it's diagonalizable, to find how to find the basis for which the matrix representation is diagonal. So kind of really from the computational side, how can we really, given some endomorphism, how can we find out if it has such a nice representation, and if it has, how can we compute it? So in the end, we will really have a method of how to do so. Now, the title of the section is Characteristic Polynomials of Endomorphisms and Matrices, and it will turn out that we can associate polynomials with endomorphisms and matrices which have a nice property, namely its zeros, so the point where the polynomial vanishes, are precisely the eigenvalues of a map. And this is good news, because even if we don't want to compute this ourselves or something, if we have, for example, if we have very large matrices, and in this case, we have a polynomial which we have to solve, and this is for solving polynomials there are methods in mathematics. We won't study them here in detail because this is not necessary for you at this point, but there are methods, and you can really find solutions of polynomials is something also computers can do. You can really find code and to compute eigenvalues in that way. So this is why it's interesting to have these eigenvalues as solutions of a polynomial equation. Now, we start off very simple. So far we have seen eigenvalues of endomorphisms, and now I want to introduce the notion of eigenvalues of matrices, which is now a direct consequence of what we did so far. Namely, we will just restrict the previous things from the previous sections and the notion of eigenvalues of endomorphisms to endomorphisms which are induced by matrices. So just this as a special case, and it will then intuitively look quite simple, I think. Now, we let n in n and take an n by n matrix, A with entries aij as usual. This shall be an n by n matrix with entries in k. Now, a number lambda in k is called an eigenvalue of the matrix A, and now very simple, if lambda is an eigenvalue of the induced map Fa, which is a map from Kn to Kn. So explicitly this means in our notation for matrices there exists some eigenvector, so some v in k to the n with v not equal to 0, such that, and now Fa of v is lambda times v, and in our shorthand notation we wrote this as A v is lambda v. So this is the simple form how you can memorize this. AV is lambda v. So this is the same as matrix multiplication, as we know, if we view this as a column vector. So this is kind of somehow making sense. Now, v is then called an eigenvector. Whoops. An eigenvector of A. So the same, just instead of mentioning the endomorphism, we mention the matrix here. An eigenvector of A corresponding to lambda. And also the set of all eigenvectors, the eigenspace. This we also denote, actually this would be E lambda of Fa, but we use the notation E lambda of A, just to simplifying things. So this would be E lambda of Fa in the previous definition. This is the eigenspace of A, so we always leave out the F here, associated with lambda. So everything just as before, but just with a direct analog for matrices here. Okay, this was A. Now part B, diagonalizability for matrices. We call A diagonalizable. So for endomorphisms, we had that we have a matrix representation of the map for which the matrix is a diagonal matrix. So if we can find some basis, and if we take a closer look at this basically means here, because the matrix representations here are quite simple, and we've seen that any two matrix representations of the same map are similar. So A is the representation of FA with respect to the canonical basis. This is kind of from the definition. And this means, so we have some matrix representation would mean we have some similar matrix here for which we get the diagonal form. So this means if we just want to leave away the endomorphisms, we can just say A is diagonalizable if A is similar to a diagonal matrix. The term similar this was introduced in one of the previous sections, so we already know what this is. So this is really a purely algebraic definition somehow, so we don't need to take maps, we can just consider matrices. Okay, now we already come to the characteristic polynomial, and first of all we define this for matrices, namely we take the following function, chi, this is the Greek letter chi, so it's, I hope this one's a bit curly, this one's just straight, I hope this is right, so for any apologies to my Greek viewers. Namely, we take a map from k to k, which should be a polynomial, and which looks like follows. So this is a polynomial we will discuss in a bit. But first of all, we just take a function which is defined straight away, namely chi a of t is defined as the determinant of a minus t times the identity matrix. So the identity matrix of size n. Okay, now if we want this a bit more explicitly, let's write down the matrix just once. So we know that A has the entries aij as I've introduced. So what happens if we subtract t times the identity matrix? So the identity matrix is only non-zero on the diagonal. So apart from the diagonal, nothing happens, or the entries stay the same. So on the diagonal, we get t times the diagonal entries there, so which is 1. So this means we just subtract t on the diagonal entries. So in the end, this matrix is just given as A11 minus t. Then A12 stays as it is, SR all the others, to A1n. In the second row, we would have A21, which stays the same. Then we would have A22 minus t, and so on to A2n. And we just go through the diagonal and always just subtract t. To AN1, AN2, and so on to, and now here in the final diagonal entry, we have again ANN minus t. Okay, so the diagonal of this thing here. Now, why is this interesting? If you recall, the last theorem in the previous section was that that something is an eigenvalue of an endomorphism f if the determinant of f minus t times the identity is 0. Which means here we just have the matrix analog, and it will turn out, we will compute this a bit, that this is also here, this is 0 if and only if t is an eigenvalue. We will discuss this in a bit. So this is kind of the relevance of this for the eigenvalues here. So we have to compute some fancy determinant, which we now view as a function in t. Okay, this is called the characteristic polynomial of the matrix A. Characteristic, oops, I can't write anymore. Characteristic polynomial of A. Okay, so this would be the main star of this section, so the main actor here that we will need in what's to come. And we will discuss this in detail in a second. So this first of all requires some remarks that are following quite directly from the definition. So that again, n in n, and that A be an n by n matrix over K. Okay, first of all, I've already explained this with the similarity of the matrix. It really follows that if you really take a look at the definitions, matrix A is diagonalizable. If and only if this induced endomorphism FA is diagonalizable. And since this endomorphism here, I mean diagonalizable in the sense of the previous definition for endomorphisms, this was definition 933. So, as I mentioned, this follows from these similarity results for the matrix representation, so I won't elaborate on this. So this is just an important observation. So it's basically these two definitions of diagonalizability, they are a good match. So they really correspond to each other. Now, this is called characteristic polynomial, but why should this be a polynomial? This is just some weird function. The determinant is some weird function which has properties, but we've seen the determinant, we have this nice explicit form. Well, nice is a big word for this, but we have this explicit form where we had this sum of all the permutations, and all we had was kind of sums of some sign times products of the matrix entries. And if you take a look at the products of the matrix entries here, we have matrix entries here. We have T as an entry, which is a variable, and we have some numbers, which are then some kind of fixed numbers. But if we take a look at this, all we can get is kind of products of these with several t's in there, might be in there in respect to these permutations, and some constant numbers. So everything will be a product of t's and of numbers and sums of this. And products of t's are powers of t. And this is why you will always get a polynomial by this. If you multiply these entries, everything will just be a polynomial in t. Since, we just get the powers of t there. This reminds me of this joke that mathematicians are really religious because they do believe in higher powers. Anyway, so by the explicit form of the determinant, chi A is the sum of products of signs. First of all, we get a sign, so plus or minus 1, and products of entries of A minus t times the identity. Hence, we find out that chi A is a polynomial in t. So as a variable of as depending on t. So this is really a polynomial. Now, if I would have the audience, this would now be a nice question to the audience. What is the degree of the polynomial? Which is the highest power that we can get? And if you take a look at this, what is kind of the highest power of t that can happen here? The highest power can happen if so again, the determinant, we had the sum of the permutation, and I explained to you this kind of Sudoku analog, that you multiply these elements in such a way that you take one element from each row and one element from each column and multiply all of them. And the only way we can do this here that we have, or the best way we can do this so that we have as many t's as possible is just if we multiply everything on the diagonal. This would be the permutation corresponding to this would be just the identity. So we would just get this times this times this times and so on times this. So we would get n many powers, n many times something with a t in there. So the highest power that will be occurring if we take this product will be t to the n times something. But t to the n is the highest power that happens here. So let me write this down a bit. So taking a look at the explicit form, the highest power of t occurs in the summand. So by summand I mean now we have the sum of all permutations, so this big sum in the summand of, sigma is just the identity permutation, and there we would have A11 minus t times A22 minus t times, and so on, A to A n n minus t. So, if we just would multiply all of this is just a long computation then, but the highest thing we get is we have the minus t times the minus t times the minus t if we multiply all of them, all the different summands with each other. So this would be, the highest power would then be minus t to the n. So this would be minus t to the n plus something, which you can also write as minus 1 to the n t to the n plus something, and this something here is a polynomial of degree at most n minus 1. So this means the degree of the characteristic polynomial is t to the n, because this is the highest power with a non-vanishing coefficient. So the degree of chi a is n. Okay, so it's a polynomial in degree n. So if we have a square matrix, we have just quadratic polynomial, and there we know from high school how to solve them. So we would basically, if we would want a zero of this polynomial, we have a quadratic equation, and quadratic equations we can solve them. So, but as you can see, if n gets bigger and bigger, so 3, 4, and so on, this might in general be not that easy to solve them. Anyway, but we will see how this can be useful and how we can do things with this polynomial. And now let me write down what I've already said, that this is really good for the eigenvalues. So this is corollary 946. This is only a corollary of the theorem from the previous section. So for n in n, A in the n by n matrices over k, and lambda be a number in k, then lambda is an eigenvalue, lambda is an eigenvalue of A, if and only if the characteristic polynomial chi A of lambda is 0. And this is just simply by taking this determinant result from the previous section for endomorphisms and just apply it to the endomorphisms induced by matrices. So this is apply Theorem 943 was this to just the map FA from Kn to Kn. And then we already have it. So this is good news. This is how we can find the eigenvalues of matrices. So for endomorphisms, this requires a bit more work, but not that much. But this is now we have a really good technique. And I want to give you an example of this. But since I don't have enough space, let me erase first, and then we see an example of how to get the eigenvalues. We consider the simple example of a 2 by 2 real matrix, so the most elementary case we have. Now, what is the characteristic polynomial of this matrix A? We can just easily compute this. So chi A of t. So we have the determinant of A minus t times the identity matrix of size 2. So we just have to subtract t on the diagonal here, which means the matrix we get is minus t here. Here it stays 1, here it stays minus 2, and there we get minus 3 minus t. Okay, the determinant of a 2 by 2 matrix, we've learned how to compute this. This times this minus this times this. So minus t times minus 3 minus t minus 1 times minus 2. Okay, let's compute this. So this here is t squared plus 3t. And this here is plus 2. So this is the polynomial. Now, to find the eigenvalues, we need to find the zeros of this polynomial. And this is something that you kind of compute explicitly if you kind of take a really sharp look at this. We can write this as a product of two linear polynomials. Namely, this is the same as t plus 1 times t plus 2. This is an elementary computation. And now this is really useful because from this we can see what the zeros are, because a polynomial or a product vanishes if and only if one of the factors vanishes. So this means we get that chi A of t is 0 if and only if. So what possibilities do we have for t? If this becomes 0, this would mean t would be minus 1. This would become 0 if t is minus 2. So we have two eigenvalues, namely minus 1 and minus 2. So minus 1 and minus 2 are the eigenvalues, so we can't have any further because we don't have any further zeros, are the eigenvalues of A. And now this already shows that the matrix is diagonalizable, because we've seen if we now again think in endomorphisms, this would be kind of an endomorphism from R2 to R2. And we saw that in endomorphism, if the number of the eigenvalues, of the pairwise distinct eigenvalues, is the same as the dimension, then it's already diagonalizable. That was a corollary. So this was corollary 942. This means that A, so first of all it means FA is diagonalizable, but we've already seen that FA is, this is what I mentioned in the previous remark, A is diagonalizable if and only if the map is, so this means A is diagonalizable. Okay, what we now still want to do is to find the eigenspaces. So how can we find the eigenvectors of such a matrix? Now, we just basically have to take these two eigenvalues, so find the eigenspaces by taking these and solving the equation that we need. Namely, find the eigenspaces by solving linear systems as follows. So the eigenvectors corresponding to the eigenvectors corresponding to -1. How are they given? They are now given as A, so the matrix A, 0, -1, +1, -2, -3. This times the vector now, I write this as a column vector, which now in R2 has 2 entries. So this vector would be xy. So this times the vector must be minus the vector. So -1 times xy. Okay, and if we now write this down and write, so if we do matrix multiplication here and just consider this component-wise, we get 2 equations, one for the first and for the second component. In the first component of the vector, we would have 0 times x plus 1 times y, which is y, equals the first component here, which is minus x. And now we have minus in the second component, -2 times x, -3 times y. So -2x minus 3y equals -y. Okay, this is a system of linear equations, and we learned how to solve them by Gaussian elimination, and then this procedure of how to get the coordinates from this. And when computes here in this setting from these 2 equations here are satisfied if and only if x is equal to y. So the eigenspace E minus 1 of A is simply given by all the spaces, all the coordinates for which, not E is equal to y, E is equal to -y. Or other way around, y is equal to -x. I mean, this, okay, it already stands here, and if you insert this there, you get the same, this is the set of all solutions. So all we get is that we get x comma minus x in R2 over all x in R. Very easy to see that this is the linear subspace of R2, and so this is the eigenspace here. And the same you could then do with the other eigenvalue. Of course, then we only would get a different system of equations, because now we would have -2 here, so we would have a 2 here and a 2 there. So again, it's a system of linear equations which we can solve, which takes some work. But then you get, and let me just write down the result. By solving the system of linear equations, we get E. I mean, it's also almost apparent from this. E minus 2 of A is now the space of all x comma minus 2x in R2, where x is in R. Okay, and here you can easily see this is only, they only intersect in 0. They only intersect in this point 0. So we have 2 one-dimensional vector spaces. I mean, these are obviously one-dimensional. 2 one-dimensional vector spaces of R2, which do not intersect. So they have to, the sum of them has to be all of R2. So here indeed we have a direct sum compositions, which you could see from these numbers. So one sees here that R2 is indeed what we know by our theoretical results, which we already knew from being diagonalizable at this point, it's E minus 1 of A, direct sum E minus 2 of A. So this is something you can really see from the numbers that are in there here. Okay, so this was really an example, and as you can tell, if you get a big matrix, you will get, so not 2 by 2, but anything else, you would get, of course, a more complicated system of linear equations, but this is something we learned how to solve. So this will always be, if you just really do this properly and really only have constancy on the right-hand side, so if you would add them to the other side and so on, this would really be always a homogeneous system of linear equations. And as we know, a homogeneous system of linear equations, the solution set of this, as we've learned previously in section 8.4, I think it was, the solution set of homogeneous systems of linear equations is always a linear subspace of, k to the n. Okay, so this is, this all works out nicely. So this is the way how we can, in principle, find eigenvalues and eigenvectors of a matrix, which is good. Now, we want to get back to endomorphisms. So we also want to find more abstract endomorphisms, which is where we will again go via matrix representations. Let me, to do so, we need to prepare a little bit for this. Namely, we only saw that if we have different matrix representations, we have seen, and if I'm talking about endomorphisms, I always take the same basis on domain and codomain, which is what we always did before. And if I take different matrix representations, we have seen that they are similar then. So, the point is this characteristic polynomial, which I can take of some matrix representation, then really independent of this representation? And the answer is yes. But for this we need this little theoretical result, namely theorem 948. Okay, let's take n and n and two n by n matrices, A and B. And so the result we need, if A and B are similar, then the characteristic polynomials coincide. And this is not that hard to show, because we've seen that similar matrices have the same determinant. And the characteristic polynomial is given as a determinant, so we just need to make one little computation to see that this works out. Namely the following. So they are similar, so assume we have, this means we have some invertible matrix S in GLNK such that SA S to the minus 1 equals B. Okay, this is definition of similarity. Now, if we take this matrix, we consider the following. We need to take the determinant of, yes, we only need one property of matrices, which was, let me do this later. We need to take the determinant of B minus T times the identity matrix of rank n. Okay, let us write this as S A S minus 1 minus T times S minus 1, because the identity matrix is just S times S minus 1, just by definition of inverses. Now, here we can see that this is now, we can further, this here can always put inside the equation, so we, inside the multiplication, so this is S A S minus 1 minus S, and now we can just take T times S minus 1, just by the properties of matrix multiplication. And now we can use this distributivity of matrix multiplication. This was this result which was actually belonging in chapter 8, which I simply forgot. This was Theorem 913. This is the same as, and now we just factorize out the S, so S times A S minus 1 minus T S minus 1. And now we can just take this term and factorize out to the other side the S minus 1. Then here we get just the identity, so this is S of A minus T identity times S minus 1. And so we see this is the map whose determinant is the characteristic polynomial of B. This is the one defining the characteristic polynomial of A. And now we see these two are similar. And as we've seen, similar matrices have the same determinants. So we're already done, because now this was corollary 915b, that similar matrices have the same determinant. Chi B of T is by definition the determinant of b minus t times the identity. This is now, by this corollary, the same as the determinant of A minus T times the identity matrix, and this is chi A of T, and this, of course, for all T in K. So, this already follows. So it's only from the properties of the determinant, and we just needed to check that this kind of, the similarity still works if we subtract T times the identity very roughly. Okay, now, this is the observation for this, and now we can now, given this result, we can now transfer again to endomorphisms. Basically, we could do the next definition also without the other thing, but this now shows how to compute this, how to compute the result that we, how to compute the polynomials occurring here. Namely, if V is some arbitrary finite dimensional vector space, over the field K, and if F is an endomorphism, then the characteristic polynomial of the endomorphism is now chi with index f now from K to K. Chi f of t is now the determinant, and now we define this as a determinant of the endomorphism, namely determinant of f minus t times the identity map on V. This is called the characteristic polynomial of f. Okay, this is what we, just defining it in this way, this is what we just considered. And we can, since determine, something I wanted to mention first. So we can now just rephrase this theorem about eigenvalues and determinants, namely, this was theorem 943. So, in other words, namely this said lambda in K is an eigenvalue of f. If and only if the characteristic polynomial of f vanishes at lambda. So this is just using new notation, no new mathematics. Now, we've studied matrices before, and if you take a look at how we defined the determinant of an endomorphism, we defined it via the determinants of its matrix representations. This is how we went. And this is also what we will do now next. We can now take a look at matrices and now matrix representations and endomorphisms, and then do further results about these characteristic polynomials. Let me quickly erase. Given what we now know about similarity of these matrices and about determinants of endomorphisms and matrices, so we can now make the corollary that I've been mentioning already, and I will not prove this because this is now an immediate consequence of what I said. So corollary 950, that V be a finite dimensional vector space over K. F be an endomorphism. And B be an ordered basis. Basis of V. Then we get that the characteristic polynomial of F is the characteristic polynomial of MBF, the matrix representation of F with respect to the basis B here. Okay, in particular, this is a nice consequence, which is maybe not completely obvious, that this characteristic polynomial of an arbitrary endomorphism between finite dimensional vector spaces, of course, is always a polynomial, because this is the polynomial, right? So this is really, it's not only called characteristic polynomial, it really is a polynomial. Okay, so this given, we now want to take a closer look at what these characteristic polynomials mean. And so we've now seen how the eigenvalues are obtained. Now the question is, what about the other term that we've studied so far, namely the diagonalizability of a linear map? So can we use the characteristic polynomial to say something about the diagonalizability of an endomorphism? And this is slightly less obvious than than this kind of computation that we had, but it turns out we really can. We can make a statement about these characteristic polynomials, and we will use them throughout the rest of this chapter to really find a really good and tangible criterion for an endomorphism to be diagonalizable. Now, theorem 951, and this is the first interesting statement here. We will see, we'll basically extend this statement in another theorem a bit later. So let n in n, let V be a vector space. V, we don't need this B here if we reduce everything. V, vector space over K, which is finite dimensional and which shall have dimension n. Then it turns out if, F an endomorphism, as usual, if F is diagonalizable, then there exists lambda 1 to lambda n in K such that, and these are indeed eigenvalues then, which follows from what I'm writing now, namely chi f of t has a very simple form. It's given by lambda 1 minus t times lambda 2 minus t times and so on to lambda n minus t. So the polynomial is then really given as a product of linear polynomials. And as you hopefully know, not all polynomials have this property. For example, if we take the real numbers, k equal to r, and we take the polynomial t squared plus 1, this has no real solutions. And over the complex numbers, we could work with that, and we will do so a bit later. But t squared plus 1 does not have any does not have any points where it vanishes. So especially, we cannot write this as a product of two linear terms. So if we would get this as a characteristic polynomial, it could not be diagonalizable by this criterion. And if we have diagonalizability, we have this, but we don't know anything about the converse at this point. Okay, first of all, let me first, let me prove this, and the proof is surprisingly simple. So if f is diagonalizable, I mean, we just need to apply the definition. So diagonalizable means we get a basis such that the matrix representation is diagonal. So we have B an ordered basis of V such that the corresponding matrix representation MBF, which is now an n by n matrix, is a diagonal matrix. Okay, and let's give the entries a name. So A is our shorthand notation for MB of F. Is now given as follows: lambda 1, lambda 2, and so on the diagonal, and 0 everywhere else. So this is a diagonal matrix. Now, what is the characteristic polynomial with respect? Now, if we can, as we've learned, the characteristic polynomial of endomorphisms and matrices, we can use any matrix representation to compute the characteristic polynomial of F. So let's take this particularly simple one. Namely, we get that the characteristic polynomial of F in T, this is the characteristic polynomial of A in T. And now, what is this? This is the determinant of the matrix that we get if we subtract T times the identity from this. And this matrix is also very simple. So we just need to subtract T on the diagonals. So we get lambda 1 minus T, lambda 2 minus T, and so on to lambda n minus T. And the rest was 0 before and stays 0. So again, it's a diagonal matrix, just by definition. So this is the determinant of the diagonal matrix, and we've seen that this is now really simple. I mean, this follows from the formula for upper triangular matrices. It's just the product of all the entries. This is just lambda 1 minus t times lambda 2 minus t, and so on to lambda n minus t. And this is what we wanted to show. This is the statement. So we just use that we have a basis with a really simple matrix representation, and we already get this nice property of the characteristic polynomial. So yeah, we can say something about diagonalizability by the characteristic polynomial, and I will first give now a remark with two properties that are worth mentioning, and then we will consider an example, and then you will see why this is really useful, or why this is how this can be used. Now, remark 952. First of all, part one, I haven't said anything that they don't need to be distinct. So we could have the same value here multiple times. So yeah, in theorem 951, lambda 1 to lambda n do not need to be pairwise distinct. So if, now let's give some different names, mu1 to mu k are the pairwise distinct eigenvalues of f, then it turns out that there are some powers, k1 to, n1 to nr, nk was this, in n, such that the polynomials of the following form. So we can just have that if we take only distinct ones, we have multiples in here. So we might have multiples of the same factor here. So all we get is kind of powers of the different factors. So if they are pairwise distinct, we would get that chi f of t is mu1 minus t to the power of k1 times mu2 minus t times k2. We just need to reorder these products, so we really get this nice beautiful product to mu k minus t, I'm using again k's, it was n's, n1, n2 and nk in here. So this is the form of the polynomial if we have distinct matrices. And it will turn out that these exponents here, so the powers with which the eigenvalues appear in this polynomial, they will play an important role in a bit. So this will be a crucial number. And keep in mind we will need these exponents later, and I will then define them and give them a name. Okay, this was the first part. Second part of the remark. The converse of theorem 951 is false. So if we know that the characteristic polynomial has this nice form, we don't know yet if the map is diagonalizable. And I want to give you a counterexample, and it's a very simple one actually. Consider the map induced by a matrix. So Fa, and now we again take a 2 by 2 real matrix. So it's from R2 to R2, where A is now simply 1, 1, 0, 1. How simple can it be? This is just a simple matrix here. So this is a 2 by 2 matrix with real entries. Then what's the characteristic polynomial of this? So the characteristic polynomial of A, which is the same as of Fa, so this doesn't matter, chi A of t. This is the determinant now of 1 minus t, 1, 0, and here we get 1 minus t again. And this is an upper triangular matrix, so we know that the determinant of an upper triangular is just the product of these diagonals. Otherwise, you can also use the 2 by 2 matrix formula. So the characteristic polynomial is just 1 minus t squared. And so we see t has precisely one eigenvalue, namely 1. So f has the only f, or say a here, not fa, has the only eigenvalue 1. Okay, now, if this was diagonalizable, so if A was diagonalizable, then we would mean, this would mean by this theorem about diagonalizability in eigenspaces, that R2 must be the direct sum of the eigenspaces. And we only have one eigenspace because we only have one eigenvalue. So if this was diagonalizable, by theorem, this is the theorem about these eigenspace decompositions, 941, we would need that R2 must be the eigenspace of, to the eigenvalue 1. So everything should be an eigenvalue of 1. And this cannot be right, because if everything was this eigenvalue, this would mean multiplying everything by the matrix A must give 1 times the vector. So A times V must be 1 times V, so just V for all. And this is not true, because this is false. So all we need to find is a vector where A times V is not equal to V. And this is, you can just try out a bit with this matrix. A times 0, 1, if we take this vector. So what would be the product here? We would have 1 times 0 plus 1 times 1. And we see already, this cannot be the vector itself. And in the second row, we would just get 1. So this is 1, 1. And this is not 1 times 0, 1, obviously. So this is not an eigenvector. This means now if we write this as entries in R2 again, 1, 1, 0, 1, 1, 1, 0, 1 is not in E1 of A, so it can't be everything of R2. So this is of the form we wanted. So this is a product of 2 linear factors, but so of 2 linear polynomials, but it's not diagonalizable, so this disproves this claim that kind of the converse would hold. Now, let's take a more concrete example. 953. And we will now discuss the same example twice, and we will see why in a bit. Now let's go 1 dimension further and take a 3 by 3 matrix, but not a very complicated one. We take 1, 2, 3. Minus 1, 4, and 0, 0, 5. So this is obviously a real 3 by 3 matrix. Okay, now, what's the characteristic polynomial? The characteristic polynomial, chi a of t, this is given as the determinant of, now let's write this again, 1 minus t, 2, 3, minus 1, minus 1 minus t, and 4, and finally 0, 0, 5 minus t. Now, we can either use now the rule of Zarus for 3 by 3 matrices. Whoops, sorry, I'm now getting messed up here. Either use the rule of Zarus and see that some summands are vanishing, or you can also use this fancy exercise, because we saw that this is now, if we write this as block matrices, we have one block here. Let me just explain this here. One block would be this one. This is something irrelevant, and this is 0. This was precisely the form where we had the determinants, namely, it turns out that if now we have zeros here in the bottom left block matrix, if there are only zeros, this is the determinant of this one times the determinant of this, and this is 1 by 1 matrix, so it's just this number. So this would be, let me check which, there was sheet 5, exercise 3a. This was where we used this, so this would be the determinant of 1 minus t, 2 minus 1, minus 1 and minus 1 minus t times 5 minus t. Okay, now we can do this computation and compute this stuff, and it turns out this is in the end, or maybe that's, we can do this explicitly, so this would be 1 minus t times minus 1 minus t minus, or plus 2, so and this multiplied with 5 minus t, and we just leave this 5 minus t as it is, because that's already part of the form of the characteristic polynomial that we would like. So this multiplied, this here gives, this is the same as t minus 1 times t plus 1, if we just add 2 signs here. So this is just t squared minus 1 plus 2 times 5 minus t, which is, so chi a of t is t squared plus 1 times 5 minus t. So, taking a look at this characteristic polynomial, this is now what tells us some things, because now we have this polynomial that I already mentioned. It's especially the same here, t squared plus 1. This is an example of some polynomial which does not have any real solutions. So this, let me squeeze a bit in here. T squared plus 1 equals 0 has no solution in R. This means we cannot write this as a product of linear factors, because linear factors have 0, so thus cannot be written as a product of linear factors. And this now helps us with this theorem here. So the characteristic polynomial, now we can again use FA if we do this in the same way. So like for so this endomorphism FA is discussed here. So we don't have such a decomposition. So by contraposition to this statement here, we get that this does not hold, so F cannot be diagonalizable. Meaning here, A is not diagonalizable, so we don't need to try to search for eigenvectors and so on, which is always some computational effort. We can just stop right here and say, no, it's not diagonalizable. The only eigenvalue here is 5, and it cannot be diagonalized. Now I want to use the same example again, but in a slightly different way after I erase the blackboard.